equations I have written on the board. So I haven't provided you with a formula sheet specifically for this unit yet. There's a total of four equations that'll be in our forces unit by the time we're done. We're at 3 out of the 4. I want to remind you that only 3 forces out of that entire list on that sheet that we did called Intro to Forces or Introduction to Forces had their own equation. Their own special equation is one way that we can solve for that value. Okay, that's only one way. And the only reason, or the only time that that works is if we have all of the information to plug into the formula. For example, you can't solve for f of g unless you know both the mass and the g. Right? If you don't know the mass, you can't solve for force of gravity. If you don't know the g on that location, you can't solve for the force of gravity. You need to know both. Same thing with the force of friction. You need to know both the mu and the normal force. If you don't know both of them, you can't use this equation. Now the reason I'm bringing that up is because any force, we can use Newton's second law to set it up. Newton's second law, the sum of all my forces, which is equal to mass times acceleration, add my ups, subtract my downs, set it equal to F net or m times a. Add my rights, subtract my lefts, set equal to m times a. We can use Newton's second law to solve for any force. Things like normal force, things like applied force, those can only be solved for with Newton's second law because they don't have their own special form. Okay, so I just want to kind of start by talking about that. So let's take a look on the back of this worksheet called Free Body Diagrams with Friction. Now, the way that these are originally worded is just like fill in every single blank on the paper. What's probably more common in a given problem would be something along the lines of a rightward force. I'm looking at the first one. A rightward force is applied to I'm looking at the first one on the back side. A rightward force is applied to a 5 kilogram object to move it across a rough surface with a rightward acceleration of 2 meters per second squared. The coefficient of friction between the object and the surface is 0.1. A typical question would then say something along the lines of, what is the applied force? And that would be the question. This is, and fill in every single blank on the free body diagram. That's kind of how this one's worded. But that's more typical. So, if you were going to say, hey, I only really care about the applied force, all I need to do is some of it, the answer would be great. If you only need to do some of it, then only do some of it. With these, it's going to be more common, though, that we're going to need a free body diagram with every force labeled. That's why I've been trying to show you free body diagrams. That's why I've been trying to say, hey, let's fill in all the forces, because those are things that we're going to be using. Girls? Thank you. So those are things that we're going to be using. So when we take a look at this, this is a pretty straightforward free body diagram. We have a box, we have an applied, we have a normal, we have a force of friction, we have a force of gravity. It's a pretty common one that we've seen so far. The thing that's a little bit different about this one is now we have a coefficient of friction. So it says the coefficient of friction is 0.1. It also tells us that this is a 5 kilogram object. I like to put that in there. It tells me I have an acceleration of 2 meters per second, which is just saying 2 meters per second squared. It's just another way to write that. And it's going to say to the right. Now, one of the things it does ask for is it asks for F net. I don't often ask you for net force, like directly. I typically don't write a problem such like, what is the net force of acting on the object? Because that's not a very common thing that's like directly asked. If you were going to be designing something or trying to figure out something in real life, generally speaking, they wouldn't say, well, what is the net force acting on? It'd be like, how strong does this cable have to be? Or how much force do you have to apply in order to move this object this way? It's more of what is the forces kind of piece, just to kind of say that. Now, if we were trying to take the approach and say, hey, let's pretend that this was the problem, and the problem asks, what is the applied force? Then we could probably go through and we could potentially skip a few steps, and we wouldn't have to have every single blank filled in. The issue is, once we start getting this force of friction equation, we need to know normal force, and to know the normal force, we have to know the force of gravity. So it really becomes filling in a lot of this stuff. So you could try it. Chances are good we're going to be filling all of those in order to get to this. So if we start with what I consider to be probably the best starting place, is we start with the force of gravity. And force of gravity, which is the same as weight, is simply when we take the mass of the object, which is measured in kilograms, so 5, times our gravitational acceleration of 9.8, so this would be 49 newtons. Got to write the dot on my shirt. 49 newtons. Now let's quick thought. Which direction is this object accelerating? The right. What's true then about my acceleration up and down? What's that?
Balanced.
What's true about the, yes, your forces are balanced. What's true about the acceleration though?
0.
It's 0, because what's true about your velocity in the y direction? It's constant, right? So my forces are balanced, absolutely. Now, because we only have one force up, and because we only have one force down, when I add all my ups, Newton's second law, I add my ups, I subtract my downs, they have to add up to 0, you just told me. So what does my normal force also have to have a value of?
49.
49. My forces in the y direction have to balance and add up to 0. Is that always the case? Does my normal force always equal my gravitational force?
No.
No, it's common, but not always. Okay, just don't automatically put it there, just kind of do the mental checklist. 1 up, 1 down, no acceleration, yeah, they're crazy. Okay, so now, applied force. In order to solve for the applied force, we have to, there is no special formula for applied force. The only way we can solve for applied force is by using Newton's second law. And when we do Newton's second law, we're going to have to add our rights and we're going to have to subtract our lefts. I'm going to need to know what this value is before I can do Newton's second law. So if we have enough information, we can use a special equation. And if we know mu, and if we know our normal force, we can calculate the force of friction using a special equation. If we didn't know mu, and if we didn't know normal force, then we couldn't do it this way. But we do in this problem. So force of friction is equal to our coefficient of friction, mu, times our normal force, and our force of friction is going to be 0.1 times 49 to give us a force of friction of 4.9 newtons. So my force of friction is 4.9 newtons. Now are my forces balanced or unbalanced in the x direction? They're unbalanced. How do we know that? Now because it's moving, because it's accelerating, yeah. Okay, an object can move without accelerating. Constant velocity. So my forces are unbalanced, and it's accelerating to the right, which means my forces are unbalanced to the right. In order to solve for my applied force, Newton's second law is required. Newton's second law says the sum of all my forces is equal to F net, which is equal to mass times acceleration. Sure. All right, so that's Newton's second law. Sum of all my forces equal F net, which is equal to mass times acceleration. Now, I haven't determined F net. I honestly don't really care about F net. If you want to, it's 10, just for the record, it's 10. You can say, how did I get that? Well, I took the M times the A to get F net, which is what I'm about to do. But I don't, F net's kind of intermediate step that I really just kind of use this. So when I sum up all my forces, now I'm talking in the x direction. So it's going to be mass times acceleration in the x direction. I add my forces that are pointing to the right. My applied force is pointing to the right. That's the only one pointing to the right. If there were more, I'd add them all. I then subtract all of my forces pointing to the left. There's one. It's the force of friction, and that's equal to mass times acceleration in the x direction. Now, if we plug values in where we have values, we get an applied force minus the force of friction, which is 4.9, which is equal to the mass of 5 times the acceleration of 2, which is going to be 10. 10, add 4.9, my applied force is going to be 14.9 newtons. My rights are 10 newtons bigger than my lefts. Now this one I gave you the coefficient of friction. A different calculation that we could do would be to solve for the coefficient of friction. And that's what that next one's going to ask you, just for the record. The only way we can solve for mu is if you know these two values. Okay. Just to kind of keep that in mind. So, why don't you try that next one? It's a similar problem, slightly different from the standpoint of this time I don't give you mu. So in the problem we did together on the board, because mu was given to be 0.1, we could calculate the force of friction. The one I'm asking you to do, it doesn't give you mu. So there's two ways you can find the force of friction. Use the force of friction equation if you have all the information, or you can build Newton's second law and you can solve for that force in it. Now I'm not saying Newton's second law is the exact same in this one as it is in that one. It might be, it might not be. But the idea is each and every time you use Newton's second law, you look at the situation you have and you build it to match the situation you have. So why don't you give that a try? If you get stuck, we'll talk about it in just a little bit. try to help you make sure we're on the right track. So this is just me kind of quickly redrawing this. This is the only force given. It says a rightward force of 25 newtons is applied. So I have an applied force. I have an acceleration, mass, a lot of blanks. Where's probably the best place to start? FG. And how do we calculate F of G?
Mass times gravity.
Mass times gravitational acceleration, which on Earth is 9.8. So this is 4 times 9.8. So my force of gravity is going to be 39.2. That's a calculation we can do because we have its own special formula and we know enough information to use that special formula. What's true about my force in the y direction? Balanced or unbalanced? So what's true, is there only one force up and one force down? So what's true about those two values? They're going to be equal to one another, right? So my normal force is also 39.2. Do I have enough information to use what I'm calling the special equation, the force of friction equation? No, right? Because do I know the normal force? Yes, but I don't know the coefficient, and if I don't know the coefficient, I can't solve for the force of friction. So then you got to go to Newton's second law, and I'll pause in a moment to let you do this. Building this equation is an important step in these problems. So Newton's second law says the sum of all my forces, I'm talking specifically in the x direction, is equal to mass times acceleration in the x direction. Remember when I sum up my forces on this intro to forces sheet, we're adding our rights, we subtract our lefts. We add our ups, we subtract our downs. I'll pause, I'll let you build that equation. That's how we can solve for force of friction, is using that equation. But you have to build that equation to match the situation we have. All right, Newton's second law. Newton's second law in the x direction. Which forces do I add? My rights, lefts, ups, or downs? In the x direction.
Rights and lefts. Or you add your rights.
I add my rights, yep, and then I subtract my lefts. Good. For my picture, what are my rights? Which ones am I adding?
Your applied force.
Are applied. Any others?
No.
And I subtract my lefts. Which ones are my lefts?
Friction.
Any others?
No.
That's it then. And I don't really care about my net force, but I can set that equal to mass times acceleration in the x direction. Of these forces, masses, and acceleration, how many unknowns do we have? Do we know the value of the applied force?
Yes.
Do we know the value of our force of friction? No. Do we know our mass?
Yes.
Do we know our acceleration? So how many unknowns do we have?
One.
Single variable algebra, right? And that's what we're at this point. This step right here is important. And it's something that we do with Newton's second law over and over again. We look at the situation, we look at our free body diagram, and we build that equation according to the situation we have. This is the situation we have here. It happens to be the same situation over there. It's a fairly common situation, but it's not always going to be this way, just so we're clear. from here you should hopefully be able to just plug in some values and solve. This is going to be 25 minus force of friction is equal to 4 times 2.5. And if we go through and we do the algebra, I'm going to trust that I did it right when I made the answer key. We get a force of friction of 15. Oh yeah, 4 times 2.5 is 10. So my rights are 10 bigger than my lefts. So 25 minus 15 is a 10. So that's how we can determine force of friction when we don't know the coefficient of friction. We use Newton's second law. The final step is how do you calculate the coefficient of friction, or mu. This is the only equation that has mu in it. So this is the equation you must use in order to calculate for the coefficient of friction. Now there may be a few times I might give it in a problem, and I might ask you what is mu equal, just to see if you can identify that coefficient of friction and mu are one and the same. It's not very, I don't think I do it. I could do it, but I don't think I do. So if this is 15, and this is 39.2, then our coefficient of friction, again, trusting my answer key was correct, is 0.383. It's a coefficient. A coefficient is a number. The units associated with a coefficient is nothing. There are no units. So it's just a number. It's 0.383. Typically, coefficient of friction is less than 1, like it is here. Why don't you try the next one again? Now this is a problem, more of a story problem, more typical question that we're going to do. I would strongly encourage you to draw a free body diagram. Leave Me Alone is sledding with his friends when he becomes disgruntled by one of his friends. He, Leave Me Alone, exerts a rightward force of 9.13 newtons on his 4.68 kilogram sled to accelerate across the snow. The acceleration of the sled is 0.185 meters per second squared, meters per second, meters per second squared. This gives an acceleration. What is the coefficient of friction between the sled and the snow? So I'm really only asking you one variable. Solve for the coefficient of friction. I'm warning you, advising you, maybe I should say, to draw a free body diagram. And I'm not saying you have to completely fill in the free body diagram, but as you kind of work through it, you're going to find that you're going to need certain things, and you can fill in what you need to on your free body diagram. So why don't you try that? No, I'm not gonna. That was my original thought of it. So the situation would be, if I were to be lifting up, but not off the ground.
If it says up could be the problem, that's a situation where is that the only one?
Yes, and so it'd be kind of weird, but like if I was gonna try to drag this, but I couldn't apply a big enough force because of the friction, if I were to lift up on it and this way at the same time, I could reduce, by lifting up, decreases my normal force, which decreases my force of friction, which then pulls, which would be kind of hard to go like this and like this. So more realistically, you would pull at some angle, but then what happens is we take that angle of force and we break it into our X and Y components. Like pulling on a rope, right? You don't pull you don't pull a sled like this across the ground. You pull it at some angle, which actually decreases your normal force level. But it'd be pretty specific. So this is what our free body diagram should look like with only the information given. Now, if our ultimate goal is to solve for this, you need to then kind of recognize, well, the only equation that has that in it is this. So if I want to solve for the coefficient of friction, I need to know my force of friction and my normal force, which according to my free body diagrams, I don't know yet. So then we have to kind of start going and, well, I have to calculate my force of friction. I'd have to use Newton's second law. I have to determine my normal force. I'd have to use Newton's second law as well for that. And we can kind of work from there. So in the end, you're going to have to figure out that, and then once you figure out that, that will help us here. But we have to use Newton's second law to solve for force of friction, so we can solve for coefficient. All right, so let's take a look at force of gravity. That's a good place to start. Our force of gravity is equal to m times g, and our force of gravity can be calculated by taking our mass, 4.68, multiplying by that, by that meaning 9.8, and then when we go through and we take 4.68, take 4.68 and we multiply by 9.8, we get a value of 45.864 newtons. 45.864 newtons. Now I'm going to try to keep as many decimal points until the very end. Force in the y direction, balanced or unbalanced? Balanced. How many ups versus how many downs? 1 and 1. So what's true about all my ups minus all my downs? They have to add up to 0. So therefore they must have the same value, right? So this is 45.864 newtons as well. That gets us one step closer to finding mu, because now we know that this is 45.864. Then it's easy peasy, of course. We just got to figure out, all we got to do is plug in the force of friction, and easy peasy, we have to solve for force of friction. Force of friction, I'm going to say, is not as easy peasy as some other things, but it is not too bad, hopefully. And we have to use Newton's second law because I can't use the force of friction equation because I don't know the coefficient of friction. And we can say the sum of all my forces is equal to F net, which is equal to mass times acceleration. And I'm specifically talking in the x direction, just so we're clear. We're talking about the x direction. I really don't care about my net force, so I often just ignore that part and I say, hey, if I add all my ups, subtract them all my downs, I can set it equal to m times a. If I add all my rights, subtract all my lefts, I can equal to m times a. And that's what we're doing in the x direction. I'm going to take my applied force, that's my right. I'm going to subtract my force of friction, that's my left. I'm going to set it to mass times acceleration in the x direction. That's how we have to solve for force of friction if we don't know mu. So my applied force, 9.13, minus our force of friction is equal to 4.68 times the acceleration of 0.815. We get an equation that looks something like that. And then you solve for force of friction. You're probably going to add force of friction to the one side. You're going to subtract the 3.8142 to the other side. So we're going to take that minus that. And we should get, hopefully, I'm doing my algebra correct, a force of friction that's equal to 5.3158. Which now I can bring over to my force of friction equation of 5.3158. Solve for mu, divide both sides, 45.864. And we get 0.115903, blah, blah, blah. Now, I wrote 3 decimals. I'll be honest, I don't know why I wrote 3 decimals because I kind of said 2 is a pretty good number. What are we doing with these? Doing okay? Last hour I had some confusion. Some people were like, how do you do that force of friction? And maybe that's the case, maybe that's not the case from you. I got some thumbs up, which is good. But that's kind of where we're at. We'll do this last one. I'll let you do it. I'll put a free body diagram on the board kind of along the way. One thing I did add to it is we could also add solve for coefficient of friction. But why don't you try this last one? Then as you kind of go, again, I'll kind of do what I just did, and hey, this is what your free body diagram, hey, this is what your value should be, hey, this is what you should do, and then that'll probably be right about the end of class. So if you haven't done the last one already, let's do this last one. We'll call it a week after that, and then on Monday we'll talk a little bit about static versus kinetic friction, and then we'll give you some time to work on a couple friction homework sheets for on Monday. So I want you to do this last one, set it up. I'll leave that up just for a little bit longer. About Ernesto and Amanda. Yeah.
Is this test gonna be before Thanksgiving?
No. Yeah. No, we won't be done with this. But
Is there more stuff after this?
springs, friction. We just got to keep. We're gonna practice friction.
So it like keeps going more and more.
We're gonna add springs.
When? On Monday?
No, not Monday. Springs will probably be like Wednesday or Thursday.
Yeah, makes sense. Sounds like a good day.
So we aren't going to test before spring break. We will test before spring break.
Dang it.
We will test before spring break.
Imagine if we had a spring break.
But we will not
That's in March.
test prior to Thanksgiving. Okay, we will test after Thanksgiving. I'm not sure how far after Thanksgiving, but it will be after Thanksgiving. So let's try this last one with Ernesto and Amanda. Thank you. I went through and I did a lot of this work on a calculator. I didn't do a lot of it showing all those steps. But if you take the mass times 9.8, you get force of gravity. Because my forces in the y direction are balanced, my ups minus my downs have to add up to 0. These two are going to be the same. Because my force of friction is smaller than my applied force, and we know that because I have an acceleration to the right, I did Newton's second law to say add my rights, subtract my lefts, which is equal to mass times acceleration. And when you go this minus this was unknown, which is equal to m times a, and we solve for our unknown, we get 28.7144. Now, if we were to go and say, and I added it, and say, well, what's our mu? Well, force of friction is equal to mu times the normal force. If we plug in our force of friction and our normal, we can then solve for mu. Force of friction gets a little tricky, in my opinion, just because we have to find out like every single force in order to get to those. Realize there are times that an object can be moving, can be sliding, can have friction without an applied force. If I take a stool, it came to a stop because of friction. Once it left my hand, there was no applied force, but there was a force of friction backwards on it. So those are some things to keep in mind. We'll give you some practice on Monday. Have a good weekend, everyone.